So welcome. This is not really a lecture so much as it is a listing of the material from each chapter that I would recommend knowing. So let's start with chapter 8. Yes. This is test 2. Yeah. Number 8. You should certainly understand the difference between a population and a sample. And a sampling design. What is a sampling design? Huh? I can't hear you. No, a sampling design. It's not a numerical. There's no math in chapters 8 and 9. Yes. Not a type of. What was the last thing you said?
Like in SRS or like
Yeah, well, yeah, it's the approach that you're taking in coming up with a sample. Your sampling design is how you're going about and choosing a sample. And in chapter 8, we had some good sample types, sampling designs, and some bad sampling designs. So the first one in the book is a convenience sample. Is that a good design or a bad design? Bad. Convenience samples are bad. The next type of sample we had, a sampling design, was a voluntary response sample. Good or bad? Bad. Bad. The next one was a simple random sample, an SRS. Good or bad? Good. In fact, how good is it? The best. We like a simple random samples. What else did we have here? We had a stratified sample. Good or bad? Good. Stratified sample is a good one. Cluster sample, which was good as well. Random digit dialing, which was bad. Those are the types of samples that we talked about in class.
Professor, you said that RNG is the same as a...
No, an RNG is just a way of generating random numbers. There's no sample there. It's just a way of generating random numbers. Using that to come up with a sample would be an SRS, and that's a good method. So the rest of the chapter 8, was about what makes certain samples bad. So what are some of the bad things that we want to be careful about when choosing samples? Bias is the big one. Which one? Under coverage.
Is it location one?
What's wrong with location? What do you mean by location?
Like you said, like where, depending on where you place yourself for the sample, it might be biased.
Well, I mean, we're going to put it in under bias. Anything that you do that might lead to bias. The wording effects, how you word the questions, the interviewer bias, who's actually doing the interview. Sorry? What was response bias again? Oh yeah, response bias. Yeah, response bias. These are all in the chat. I didn't make any of these up. These are all in chapter 8. And you can certainly look them up, and they're all bold. I mean, basically everything I just listed, if you go through chapter 8 and you look for anything bold, it's going to be there. Other than cluster was not there. I added cluster myself because I think cluster is an important sampling design, but the book does not mention it. So that's chapter 8. That's the entirety of chapter 8. There's no math questions from chapter 8. It's going to be conceptual. All of 8 is going to be conceptual. And then we move down to chapter 9. Chapter 9 is also conceptual. And chapter 9 talks about the difference between observations or observational studies and experiments. Before we go on, a few people came in late. Ariana, Emma, Alan, Alanis, Angel, Jonathan, Alexis, Prince, Christopher, Sarah, Itai, and Miguel. Which one? Miguel, absent. Oh, Tardy. Itai, Tardy, Christopher, Tardy. Okay. So observational study versus experiment. In general, what's better, an observational study or an experiment? Experiment is always better. Well, not always, but experiment is usually better than an observational study because you have control. In an observational study, there could be other factors that are beyond your control. You might not even know about them. Whereas in an experiment, you get to control as much as you can. So we like experiments, but of course, that doesn't mean that observational studies do not have their place. If I'm curious about the effects of smoking on children, mothers who are pregnant, who are smoking and drinking and doing drugs and how that affects their children, it might not be the best idea to have an experiment where I say, okay, you 100 women, you guys do drugs, and you 100 you smoke, and you 100 drink, and you 100 do both of those, and you 100 do all three, and let's see how the kids turn out. That might not be the most ethical. I kind of get the feeling that my mom went through an experiment like that once, but I don't know. Okay, whereas an observational study, you go to the hospital and they say, yeah, we have this unfortunate situation where the mother was on drugs and whatever. And then it's after the fact, hey, let's just follow up on the kid and see what happens. That happens, studies like that happen all the time. So whereas an experiment would be better, observational studies certainly have their place. What are some things that we worry about in either observational studies or experiments that we try to eliminate as much as possible in experiments?
Like the two variables you're using getting mixed together?
Yes, we call that confounding, but not the two variables, because usually you have an input variable and an output variable. Let's change this and see how this is affected. That's the thing that we're looking for. But if there's other variables that have an effect on that, that's what we're worried about. We want to see what this variable does, but these other ones also might have an effect. Confounding, yes.
I think just usually, like, if it includes it, it's most likely bad. That's something we should eliminate.
Yeah, which is why in experiments, you try to eliminate it. Yes.
So does that mean there should only be two variables we're looking at?
Well, as much as possible, you can't eliminate variables. There's always other variables. But we want to eliminate or control as many of them as we can.
But we're only looking at like two at a time.
Usually you're looking at an input and an output. How does this affect that? Well, this affects it, but so does that, and that. Well, if I can somehow eliminate those, great. I'll end up with a better relationship between these two. If I can't eliminate them, I have to worry about the fact that maybe they had a really big role to play and I'm not considering that. Yes.
The times when like they both affect the outcome.
Yeah, when you have like, if I say, I notice among children that the taller children tend to be able to read better than the shorter children, or those children with bigger feet tend to be able to read better than the children with smaller feet. I like to examine the relationship between foot size and reading level. And I examine that and I see that sure enough, children with bigger feet read better. It's amazing, right? Why do you think children with bigger feet read better? Because they're taller.
Because they're older.
Because they're older, not because they're taller. Fact doesn't read very well, but they're taller. Sorry, they're older. They're older. So there's a variable that's lurking around there that we might not be considering that is confounding the data. It's obfuscating our relationship.
But is that conclusion wrong?
The conclusion is not wrong, but the cause and effect relationship that you're trying to conclude is wrong. Okay, you can't say people read better because they have bigger feet. Okay, children read better that have bigger feet because they're older, they have more education, they're 2 or 3 years later and so on. That's why they read better. Yes. Okay, good talk. All right, so in an experiment or observational study, the individuals that you're studying have a name. We call them something. What are the individuals? They are the subjects of the study. And the various variables that play a role in the outcome are called the factors. All right? Is this a factor? Is that a factor? This is actually a word that you hear in English. factor. It's just, it means exactly the same thing. And then when I do an experiment, I might apply different treatments, different types of medicine, different approaches, different, whatever the case may be, to different groups of people, because I want to see how the different treatments affect the overall outcome. So individuals, factors, subjects, treatments, these are all bold-faced words in the chapter, and they are all important. When it comes to an experiment, what is the best type of experimental method we want to use? We want to have randomization. So we don't want to, I don't want to just say, okay, everyone can volunteer. 10 of you volunteer for this treatment and 10 of you volunteer for that treatment. I don't want that. I want to randomize the treatments. You don't get to pick which one you get. We're going to randomize it. What else do we want besides randomization? Replication, which means what? Not just you should be able to reproduce it. That's something that's important. But my experiment should have replication, which is I should do it multiple times. The more accurate, the more times you do it, the more accurate it's going to be. So I don't say, well, I'm going to have this treatment and that treatment, and I'll do this one for one person, this one for one person, but rather I'll do this treatment for 100 people and this one for 100 people. So I'll have, what's the purpose of that, by the way? Why do it for multiple people? Why not just do it for one?
The higher the number that you do it on, the higher the probability of success, right?
Well, what exactly is success?
Like accuracy?
Okay, so why is it more accurate to do more people? The answer is, in the law of large numbers, but not exactly. The reason for accuracy, the reason why we do replication is because all of those other factors that we can't control, we would like to average out. In other words, I can't control, how much sleep people get the night before the test, whatever it's going to be. But if I do lots of people, some will have less sleep, some will have more sleep, some will have right in the middle, it'll average out. So the more you replicate, the more likely it is to average out all these other factors that I can't control. When you do a randomized comparative experiment, that's one where you randomize your subjects to different treatments and then you compare the results, a randomized comparative experiment. You should have a control group. What's the control group? Your powers of observation astound me. What is the control group? No, the one not getting the treatment. No, it's not. It's actually exactly the opposite what you're trying to say. So it's not the same thing. But if I want to test a new medicine, I believe that this new medicine that I'm creating will cure headaches better than the old medicine. So I'm going to give this treatment to 100 people, and I'm going to give the old medicine to 100 people. That old one, that's the control group. That's the one, the status quo, the previous method, the one that we all expect to be the mainstream approach. And I'm going to do a new one and compare it to that.
What's the name of the new one again?
The treatment groups. So you have the control group, and then you have the treatment groups, if there's more than one. What does it mean? This is a term that we talked about definitely in hypothesis testing. What does it mean for a result to be statistically significant? Probably the most important term of the chapter, statistically significant. What is a statistically significant result? I am so immensely proud of my teaching that everyone got this right. Wow. What is a statistically significant result?
This is still chapter 9, right?
We are still in 9, yes. Okay.
It's a.
Good talk, man. Good talk. So a statistically significant result is one that is unlikely to have occurred by chance alone. A statistically significant result is one that is unlikely to have occurred by chance alone. If I flip a coin 100 times and I get 100 heads, a fair coin, that is. Could that have happened? Could that have happened by chance alone? Is it likely to have happened by chance alone? Then it is a statistically significant result. What do I conclude when I get a statistically significant result? What? If I flip a coin 100 times and I get 100 heads, which is a statistically significant result under the assumption that the coin is fair, what would you conclude after getting 100 heads in a row? The coin is not fair. The statistically significant results are the ones that make you question your underlying beliefs. This is the whole basis of a hypothesis test. Oh, I have this underlying hypothesis. Let me do a test. Oh, I got a statistically significant result. That's one that is unlikely to have occurred by chance, and yet it occurred. So what will I do? I will question my underlying hypothesis and say, you know what? I think it's the other hypothesis that's correct here. That happens when you have a statistically significant result. Hi, what up, girl? What's up? You're late.
I'm sorry.
Are you really sorry?
Yeah.
Okay, thank you. Appreciate that.
Thanks for understanding.
Okay. Well, I didn't say I understood. All right, so when you do experiments and you have the control group and you have the treatment group, is it good for the people in the groups to know which group they're in? Is it good for the person administering the treatments to know who's in which group? No. So how do we do an experiment where both of them don't know? Double blinds. Double blind experiments. Neither the participatory person or the one who is administering the treatments knows who is in what group. Nobody gets special treatment. Everyone is treated equally. Then we had other types of designs in chapter 9, like for example, a block design, where you kind of break up the people into blocks of similar attributes. Block design, again, to eliminate possible factors. And then within each block, you still randomize. So you're still going to randomize. You can't not randomize and have a good experiment, but you randomize within the blocks. So for example, if I want to know how this new COVID vaccine works, I might check out adults and children separately, or males and females separately, or those who have had COVID before and those who have not separately. Block them and then apply it randomly within each block to see, whatever it is I'm trying to conclude. We also had a matched pair design. What's a matched pair design? When you pair treatments up in ways, good talk. Right. So what's a matched pair design? He was, what? Sorry, I just, I threw up in my head. Say that again. Okay, good. Thank you for that. Can you be a little more explanatory with what a matched pair design is?
Let's say if one group bananas from the other strawberries, and you take a strawberry banana shape and you give that one to the other group, you know?
I didn't know it was possible to have a headache this big. A matched pair design is like a block design where your blocks are very small. They're pairs. You match a treatment and a control to a pair that have very similar attributes. That's it. What does that look for? What is happening right now? Yes?
Yeah, I have a question.
Yeah.
So, like, can you say a matched pair design, basically a block design, but when you
I'll take it. I'll take it. And then you randomize within each pair. It's a very small block.
So what would that be like in an example?
An example of a matched pair design?
Yeah.
Suppose I want to know. I have to think of one. I don't know. Let's see. Is there one in the book?
And it's like when things are similar, right?
Well, you have a pair that's similar. In particular, here's one. Does talking on a hands-free cell phone distract drivers? Undergraduate students drove in a driving simulator equipped with a hands-free cell phone. The car had brakes. How quickly does the subject react? Let's compare two designs for this experiment. So in the matched pair design, all subjects drove both with and without using the cell phone. So we paired up with and without. That was the match. That was the match pair. Each person drove with and then drove without. Randomly, which one was first, but each person drove both ways. As opposed to just having 40 people and saying 20 of you go this way, 20 of you go that way. So then we matched them up into pairs.
You do like a smaller sample size than you would normally do.
I mean, that's always your choice, but I mean, like if I'm curious,
No, I mean, like, it works the same way. As let's say you have 1,000 and 500 go to A treatment, 500 go to B treatment. And if you want to do the match treatment, you only get 500.
then yes. Yeah, you have half the number of people and just as many experimental data points, so why not? Sounds good to me. All right, so the next chapter is on data ethics. We didn't do that because nobody has ethics today. And we skipped chapter 10, which was a review chapter. And then we went to chapter 11. The last two chapters, very conceptual. The next chapter is very mathematical. Starting with probability. What are some terms that are somewhat synonymous with probability? I don't like random. No. These are terms that occurred in our discussion of probability. I'm looking for terms that are synonymous with synonyms of probability that essentially mean the same thing. No. You're just looking at words. No, think about it.
Are you the two rules?
No rules. No rules. A word in English that I can interchange with probability and mean the same thing. What? Stop looking down at your paper and reading words. You're not going to find it there. Chance. What's another one? No. Possibility. What's another one? Likelihood. These are good words. The probability of an event occurring is the chance that it occurs, the likelihood that it occurs. Possibility, it doesn't really quantify it. So I take that back. But likelihood and chance, I like those words. How likely is it that I get a heads if I flip a coin? 50%. What's the chance that I get heads? 50%. What's the probability that I get heads? 50%. Same words mean, for the same thing. But all the other words, even possibility, what's the possibility that I get heads doesn't really work. Getting heads is a possibility, but there's no numerical value for it. So probability, chance, likelihood, these are synonyms. Now, when do we use probability? In a situation where we do not know the outcome before it occurs. Which one? The whole thing. When do we use probability? In a situation where we do not know the outcome before it occurs. Rolling a die. Do I know what I'm going to get? Really? Do I know what I'm going to get? If I did, I would not be here. I would be in Vegas somewhere. Okay. Same thing with picking a card from a deck. I don't know what I'm going to get, but I know what I might get. Flipping a coin. Having a child. Boy or girl. Will it rain tomorrow here in Northridge? Yes or no? Will I win my tennis match this weekend?
Yes. No.
Yes, I play tennis. It is awesome. I don't know why everyone else is playing tennis, but I've been playing tennis for a long time.
King Richard.
King Richard, who?
William.
Oh, that one. King Richard the Slapper, got it. So, I did not watch it. I'm not a big fan of the Williams sisters personally. But nevertheless,
Why don't you like him?
their behavior on court when things do not go their way is not really endearing. So,
Are you talking about Will Smith?
yes, that's exactly who I'm talking about right now. Yes, yes, Will Smith. Excuse me? Which side of that reenactment would I be on? I'm just curious. Chris Rock's too funny. I can't be Chris Rock. I'll be Will Smith if you want. Will Smith, right? His name? Will Smith, right? Forgot his name for a second. Anyways, the question is, these are all situations where we don't know the outcome before it occurs, but we might know the outcome. These are all situations where you want to use the mathematics of probability. When do you not want to use it? You do not want to use probability when you know the outcome in advance. There's no need for it. It's silly. What's the likelihood that the next person who walks through the door is alive? It's a silly question. Of course, it's 100%. The next Do I think ghosts exist? No. Do I know that ghosts don't exist? No. They might. I just don't believe in them. I do not believe in the supernatural.
What about aliens?
I do not believe in aliens. If they show up tomorrow, it's not going to shatter my whole philosophy. I'll just say, okay, I was wrong. They're there.
So
You know,
we're the only living thing.
I personally believe that, yes.
What about God?
What about God? Do I believe in God? Yes, I believe in God. Well, this is far afield. It's not the time for it. But if you want to have a philosophical discussion later, I'm certainly down to have a discussion about it.
Philosophy 140.
Or any of the other courses. Anywho, so probability. We do not know what will occur, but we know what might occur. What do we call the collection of things that might occur? We have a name for that. No, the sample space. Every experiment, every random experiment. By a random experiment, we mean one whose outcome we do not know in advance. Every random experiment has a sample space that is the collection of all possible outcomes. What do we mean by a probability model? What do we mean by a probability model? No. What two rules? Oh, no, you're talking about something else. Well, yes. I didn't know what you meant. Those two rules certainly play a role. Well, so what is a probability model? It is an assignment of probability to every outcome in the sample space such that those two rules that you're mentioning are satisfied. What two rules must be satisfied?
Can't be negative.
What is it that can't be negative?
Probability.
Which probability? That's the thing about the word it. You can make it seem like you know what you're talking about by saying the word it, but not really. So it's very careful. What is it? Yes.
There can be a possibility of there being a negative outcome. Or like a negative probability.
Okay. None of the outcomes could be assigned a negative probability. And
Probabilities have to add up to 100.
And all of the probabilities must add to 100%. To 1, huh? 100% is 1. As long as those two are satisfied, it is a valid probability model. Being a valid probability model does not automatically mean that it conforms with reality. If I have a coin and I assign 0.8 to heads and 0.2 to tails, is that a valid probability model? Yes. Yes, they add to 1 and they're not negative. Does it conform with reality for a fair coin? No. But it's still a valid probability model. It just doesn't do anything for us. So what are the rules of probability that must be satisfied? There are a number of them, but I think we listed 4 of them. 1, probabilities must always be stuck between what 2 numbers?
0 and 1.
0 and 1. 1 means? No. 1 means?
Yes, valid.
In this context, a probability of 1 means? Which means? Likely to happen? It's guaranteed to happen. Guaranteed to happen, at least at this level. There are situations where you can have a 0% probability of an event and still have it occur. We're not going to worry about those situations in this class. What is a 0 in this class? What does a 0% probability mean? Huh? Me or you? Me or you? You? If you want, I can. I mean, some girls in this class, I can ask them if any of them are interested. You're a wingman. No, you're too shy. That's why I do it for you. Huh? Okay. You tell me what you're looking for in a girl. You know, be respectful. You know, long term, and I'll see what I can do for you. Okay. All right. Okay. Meanwhile, all joking aside, what does it mean for a probability to be 0%? It cannot happen. Okay, what is the probability of rolling a die and getting a 26? It's not possible, it's 0. Sure, but the probability is 0, numerically. What is the probability of getting something in the sample space? 100%, because the only possible outcomes are in your sample space. So it's guaranteed to occur. If 2 events are disjoint, what does disjoint mean, by the way?
Can't occur at the same time.
Can't occur at the same time. Then what's another way of writing the probability of one occurring or the other occurring? P of A or B equals? P of A plus P of B, the likelihood of A plus the likelihood of B. You can separate them and do them separately. P of A plus P of B. This is in the book. We did it in class. And finally, what is the probability of an event not happening? What's another way of writing the probability that an event does not happen? No, not A or B. It's a whole different thing. Just one event not happening. What is the probability that event E does not happen? Yes, Calvin?
1 minus the event.
1 minus?
1 minus the event.
How do you subtract an event?
A.
How do you subtract an event?
Probability.
Okay, the probability that an event does not happen is 1 minus the probability that it does happen. The likelihood that you do not get a 1, if you roll a die, what is the likelihood that you do not get a 1? 5 out of 6, which is 1 minus the likelihood that you do get a 1, which is 1 minus 1 over 6. They're the same. Magic. I did a problem today. I was tutoring someone in probability, and it was a good question. It was, you had a sequence of stoplights, and each one had a certain likelihood of being green when you get there. And the question is, what's the likelihood that at least one of the lights is green on your route? That at least one of them is green. Well, at least one of them is green means either one of them is green, or 2 of them are green, or 3 or 4 or 5. That's a lot of calculations. At least one is green. So it was easier to do the opposite of at least one being green, which is the opposite of at least one being green. None of them being green. It's one situation. You calculate that, 1 minus that, there's your answer.
So you only calculate it for 1.
You only have to calculate it for 1.
What about all of them?
None of them being green is all of them. The likelihood that none of them are green This is the opposite scenario of at least one of them being green.
So what's the formula?
The probability of E prime the probability of E prime is 1 minus the probability of E. Thank you. Sometimes I amaze even myself. Okay, next. Some situations in probability have finitely many outcomes, and some of them have infinitely many outcomes. The dice rolling, the coin flipping, the children, the rain, the cards. These are all scenarios of finitely many outcomes. Can we think of a situation that has infinitely many outcomes?
Isn't time?
Time is infinitely many outcomes. How, well, what exactly is your question or your situation where people is infinite? Probably more often than that. But again, what is your random experiment that you're dealing with?
How many people?
How many people are Greek? What? I need an experiment.
You said whatever was infinite. so
No, no,
I
no.
said
Time, if an experiment is how long am I waiting for the bus? You could wait a second, a half a second, a third of a second, a fourth of a second, a fifth of a second. Time can be subdivided into infinitely many tiny increments.
Well, then, yeah,
So-
then you just say, how many people like chicken?
How many people like chicken?
Because you got like.
How many people are on the planet?
Why?
No, it's not infinite. It's like 8 billion or so. That's not infinite.
But the time is contained is infinite,
No, stop. You're confusing me. Yes,
Something like the thing with,
distance.
like the example you gave with like throwing a free court shot, like how many shots did it take?
Yeah, if I shoot baskets until I hit, I can hit the first one. I can miss, but hit the second. I can miss those, but hit the third. I can miss those. In theory, it could be any number of them. There's no one number where you say, that's it, it's gotta be done by this point. There's always another possibility, and another possibility, and another possibility. The difference between those scenarios is that your scenario is infinite, but it's continuous infinite. You can continually subdivide and break up into smaller and smaller pieces. Whereas that one is infinite, but it's discrete, 1 or 2 or 3 or 4 or 5. It's infinite, but there are breaks in between. From a mathematical standpoint, we treat those scenarios extremely differently. In this class, we don't do any math other than the just finite, so we don't have to worry about it. But you should know that they exist. We did talk about 2 continuous models in this class. 2 continuous probability models. One we've used over and over again at this point, which is the one that we've used continuously, the normal probability model, which is the one that we've used sparingly, probably more so for homework than for anything else. Which continuous probability model did we have we used besides the normal? That is the uniform. It's the one that has the same likelihood of occurrence for all scenarios. So if I say I'm waiting for the bus and it can come anytime between now and 10 minutes from now, with equal likelihood of being at any time, that will be a uniform because it's the same likelihood everywhere. So definitely know the uniform distribution. Definitely know the normal distribution.
When you say no, do you mean just a kind of define it or?
How to calculate things with it. If I say, what's the average of the uniform distribution? How do you find the average of the uniform distribution? If I say the bus can come anytime between now and 10 minutes from now, and we're dealing with a uniform distribution, what is the expected time of arrival? So you're saying if it can come anytime between now and 10 minutes, I expect it to come in 10 minutes.
0 to 10.
5 minutes, right in the middle. on the average, sometimes in the early part, sometimes in the later part, but if it can come anytime with equal likelihood between 0 and 10, then on average, it'll come at 5.
So that's an example of a uniform probability model, right?
That's an example of a uniform probability model.
What about a normal probability model?
Well, we know where the mean is for the normal. We've done 1,000 problems with normals.
Oh, so what's an example?
What do you mean what's an example? Every homework problem was normal, right? What does normal curve look like? The bell curve, right? We've done 1,000 problems by now of those. Where's the expected value? Where's the mean of a normal? Right in the middle, the highest point. Not because it's the highest point, but because of symmetry. It's the tipping point. Remember, the mean is the tipping point. If I have a uniform distribution, so it's got the same height everywhere, where's the tipping point? Where would I put my finger? Right in the middle. Right? Right in the middle. Okay. That takes us to the end of chapter 11. Then we skipped ahead to 15. In 15, we start the main portion of the class, which is inference. The reason why we do any statistics, the purpose of it is to take samples, which are a small piece of the entire population, and then say, based upon our small sample, what can I conclude about the entire population? I want to infer something about the entire population from my sample. Thanks for the info, dude. So, the first distinction we made between populations and samples was the difference between a parameter and a statistic. What is the difference between a parameter and a statistic? Yes?
Population.
Represents the population?
No.
I'm hearing, I'll tell you, hold on, what? Of. Okay, it's amazing what one extra word does. A parameter is a numerical value characteristic of the population. Something that describes the population, like the population size, the population average, the population standard deviation, the population maximum, the population minimum. These are all numbers that describe some aspect of the population. What is a statistic? What? I got you, girl. Okay. A numerical value characteristic of the sample. The sample average, the sample size, the sample standard deviation, the sample max, the sample min, the sample this, the sample that. If it comes from a sample, it is a statistic. The first statistic that we talked about of major importance was the sample proportion. How do I calculate the sample? First of all, what letter or symbol do I use for the sample proportion? P hat. And how is P hat calculated? Right, number of successes over number of trials, X over N. P hat. What is P hat trying to measure or trying to approximate? The population proportion, which is labeled by P. So P hat is the sample proportion. P is the true proportion. Do I know P?
No.
Will I ever know P? No. If I did, why am I taking a sample? Example. So what does the law of large numbers, not to be confused with the law of big numbers, say about proportions, or specifically sample proportions? Don't just read. No, your speaking privileges are revoked. Yes.
The larger your sample size, the more likely the sample proportion is to be accurate to the actual proportion.
I'll take it. The larger your sample size, the more likely that your sample proportion is in the vicinity of the true proportion, which is why we like to take large samples. In a more mathematically precise way, we would say that as n goes to infinity, the sample proportion approaches the true proportion in a asymptotic sense of those who might have had the language of calculus. Now, your original, the population has a distribution. If I'm looking, thank you so much. If I'm looking for the average heights of every American.
What was the question?
We were just waiting for you to come back. I didn't want you to miss anything.
Oh, I mean, I got chapter 50 done.
Okay, cool. So if I'm curious about the average height of every American, and I look at every single American, is there an average height of every American? Is there a true value that I don't know? Yes, at this moment in time, right now, there is a true height. There is a true average, correct?
Yes.
That does not mean that every American has that height. There still is a distribution. Some are less, some are more. And I can draw like a histogram of all the true heights, and it would have a shape. And then I can model that shape by a curve and say, hey, this is the true population distribution for heights of Americans. Most of them are here, not that many here, very few here, and so on. If I take a sample of a certain size, and I take the average of that sample, that will also have a shape. I'm not going to get the same value for every sample, which means it's also going to have a range of possibilities and have a certain shape. How does the shape of the sampling distribution compare to the shape of the original distribution? It might be similar. Might be similar, but it has a few, three in fact, distinct features. Yes?
Is it taller?
Not necessarily. One, it has the same expected value. The mean, the average of the original is the average of the sampling distribution. That's number one. Two,
It would be flatter and wider, right? Like-
no, it will not be wider. In fact, it'll be thinner. Because as my sample size goes up, I expect to hone in on the true value, which means more and more of my values will be close to the true value as opposed to farther away. So the sample standard deviation gets smaller and it gets thinner, thereby making it larger or taller, most likely.
What, I mean, it's getting thinner.
I said your speaking privileges are revoked. And three, so what were you saying?
But if it's getting thinner, doesn't it have to get taller, like you mentioned?
No.
No.
Okay, yes, it does. I just don't want you to, I didn't want to have to agree with you. But yes, but don't worry about that. We're not going to worry about that. Three, the shape of the sampling distribution looks like what if n is large enough? It looks like a bell curve. Even if the original distribution is not normal, if n is large enough, the sampling distribution looks normal. And therefore, we can use our normal CDF button on our calculator, even in a situation where the original distribution is not itself normal. And remember what we call this theorem that says we can do this? No, the law of large numbers is something else entirely. The central limit theorem. As they say in Hebrew, it's muy importante. Now, what is the formula for the mean of a sample proportion situation? P hat, yeah.
Equals,
Well, P hat doesn't equal anything. The expected value of P hat is equal to what?
it's something over mean.
No, it's not, but thank you for playing.
Square root.
Nope,
X over n.
nope, no. X over N is not an expected value. X over N is the actual result. I'm looking for the expected value, the mean of the P hat distribution. P, the mean is the actual mean. But the standard deviation gets smaller as N gets larger. So that one we need the formula for. What is the formula for the standard deviation of the p hat distribution? Yes. The square root of p times 1 minus p over n. This is on page 340 in the book. Very important formula. We'll be using it a lot. When do I use normal CDF in this scenario? Because this is not a normal situation. These are proportions. So when am I allowed to use it? Yes?
But when you want to find like.
No. What condition must be satisfied so that I can use the normal CDF and get accurate results?
Rule of thumb.
Which rule of thumb? I can't hear you.
Can you use the normal CDF?
Louder, please. I'm sorry. It's hard for me to hear.
But you can use the normal CDF, you said.
Yes.
And you can use the normal rule of thumb.
What rule of thumb?
What do you mean?
Well, you can't just use the rule of thumb. I got to know what the rule of thumb is.
Only use if NP and 1 minus B are greater or equal to.
That's what I'm looking for. You can only use it if NP and N1 minus P, i.e. the number of successes and the number of failures, are both greater than or equal to 10. What happens if they're not both greater than or equal to 10? We use a different one if we're allowed to use that one, which we'll get to in a minute. In fact, I think, are we there already? No, next chapter. So that's it for 15. Now, 16. Confidence intervals. Confidence intervals. What is the formula for a confidence interval for P? I know, which is why we're getting a confidence interval for it. What is the formula for the confidence interval for P? P hat,
Z score,
Z star,
Z star. Or with the square root of P hat, 1 minus P over N.
you say P hat 1 minus P over N?
P hat 1 minus P hat over N.
Okay. It's P hat plus, this is in the book, P hat plus or minus Z star, square root, P hat 1 minus P hat over N.
And that's the what?
The confidence interval for P.
I thought it was the margin of error.
No, the margin of error is the thing that you're adding or subtracting. That's just the part on the right. That's Z star square root P hat 1 minus P hat over N. That's the margin of error. That's what you're adding and subtracting. Yes.
Is that if it's more than that?
You can only use this if NP and N1 minus P are greater than or equal to 10.
Is it P or P hat?
P hat, sorry, P hat. Because we don't know P, so how can you do NP? Doesn't make any sense. Cool story, bro. Now, what happens if N times P hat and N times 1 minus P hat are not both greater than or equal to 10? What do we do in that situation?
Only square figure Z,
Huh?
Z star greater.
Actually, we don't. Z star stays the same. The change is not to Z star. What's the change that we make? We don't, we only have a sample, right? All we have to go on is our sample. So we can't make changes to the population. Yes?
Would it be sample size?
Well, I can always take a new sample if I wanted to. But if I have the sample that I have, and I look at number of successes and failures, and they're not both greater than or equal to 10, and I want to use this sample, what do? Yes. I use P twiddle. P twiddle plus or minus Z star square root of P twiddle 1 minus P twiddle over N plus 4. What is P twiddle, by the way?
Is that the P?
Yes, the P with the squiggly, huh?
X plus 2 over N plus 4.
X plus 2 over N plus 4. Even if you don't get why we do it, just have these formulas on a cheat sheet. Have them written down. What are the conditions for using this one? No.
If they're not both greater greater than or equal to 10.
Well, if they're not both greater than or equal to 10, we might want to use this, but this one also has its own condition. What is the condition that must be satisfied for this one?
Plus 4.
Yes,
Greater less than 10.
if n is greater than or less than 10, did you say? Greater than or less than 10, so only not 10. Greater than or equal to 10. As long as the sample size is greater than or equal to 10, you can use this one as opposed to the original. What if the sample size is not greater than or equal to 10? What do we do then? Get a new sample. You are SOL. You cannot do these confidence intervals with any reliability. SOL means you are shit out of luck. Okay, you were 10 years old when you learned that? There you go. You were this minute old. Okay, I love it. Now, last thing in chapter 16. What if I tell you in advance, hey, I would like a margin of error of yay size. I want you to take a sample, but I don't want your margin of error to be too big because then I don't have reliable results. I want your margin of error to be that size. I tell you in advance what margin of error to use. And you say, okay, well, in that case, I will need a sample size this large. How do you calculate the size of the sample, knowing in advance what margin of error you would like to use?
One proxy interval.
Yes.
Can I just burn it out? It's really stupid to read out loud.
What am I writing? I know what to write.
N equals
N or M?
N
N.
equals Z star squared times P star open bracket
P, what? I can't do this.
star.
I'm getting blood rush to my head. Okay. Ah. Oh my God, it sucks. Okay, so what is it? N equals what?
N equal to Z star squared times P star times closed brackets 1 minus P star over M squared.
Okay. What is P star? We have P, we have P hat, we have P twiddle. What is P star, huh? What is P star? Oh, I gotta have this. What is P star?
Wait, what is this?
This is for figuring out the sample size. Yes?
Any previous knowledge of P that we have.
Okay. If we have any previous knowledge of what P might be, like, hey, 2 years ago, somebody did a similar study and they had a P of 0.362. Well, in that case, go ahead and use 0.362. But what if you don't have that information?
Use 1/2.
Use 1/2. You'll have a larger sample size, but you'll cover all your bases. So that takes us to the end of chapter 16.
So you give us the margin of error, the sample size will be.
No, the sample size will be given by that formula. How can I have a sample size of 1/2? It might be. That's the sample size right there.
So that's the formula for final sample size.
Can't get anything by you. Okay, so. Oh, and I'm on video, so sucks to be me. All right, 17. And which formulas?
The calculator way.
Like what the calculator does? It's all in the book.
The different ways we calculate.
Are you asking like how to learn how to do these on the calculator? Well, I did them all in class, but if you,
I forgot my.
no, what I would do is whenever I want to learn something new on a TI, I go on YouTube and I type in, how do I do this? And someone's made a video of it, and then I'm like, oh, hey, I learned something new today. What?
You posted all the lectures up to 17, right?
So,
Yeah.
yes,
And say, is what I said about the one property interval wrong?
yes. Okay. Chapter 17, what? It's up there. I promise. Which one, 17 or 15?
15. It's not up there.
Yeah, it's
Shut up, you. So which one? Hold on. Oh, if I have video problems, I have video problems. Hold on. When I look at my videos, what do I have here? I have lecture 15, 14, 13, 12, 11. I'm missing 10 because that was the one that I had bad. Everything's up there. Well, because I put one up like right before class today. Did you check during once class started? No. Okay, so this is on you. Whew. Okay, fine then. I actually have a comment on one of them. And he said 100, 100, 100. Mark Pacheco. Mark, thank you. I don't know how to reply to that, but nevertheless. Okay, chapter 17. Is that what I sound like? Wow, I hate my voice. How do you guys put up with that? All right, turn it off. All right, I said turn it off. Jeez. Okay. So, chapter 17, hypothesis testing. What are the two basic forms of hypothesis testing? No. The two basic types of hypothesis testing are what? You guys are just like looking for words written down anywhere on the page where I wrote two things. You're assuming that's the answer. It's one-tailed versus two-tailed. The two basic forms of hypothesis testing, one-tailed and two-tailed. Yes, it is. Hypothesis tests and test of significance are the same thing. What?
It was the same video twice. You just labeled the lecture.
What? I did not.
Yeah, 14 and 15 was the same. lecture.
Shut up. Hold on.
Plus 17.
Quiet. Oh, shit, I did. I might not have it then. Shit. Wait, March 17th was the last day that we had class. We didn't have class last week. I have one up March 17th.
Yeah, but we did chapter 15 before that.
I know, but I have March 17th, I have March 16th, which has been those two that week. Oh, March 8th, I have one, so I'm missing like a March 10th one. That might have been the one that I had computer problems. Yeah, that might have been that one. All right, yeah, so whatever, that's what it is. Okay. So sorry. Let's move on.
Can you push the videos from the previous classes, like from the lesson?
Sure. I have all my, I mean, I don't remember the dates and which lectures are which, but I taught the same stuff.
Okay.
So yeah, if you want to go back to a previous year, you'll find things. Yeah. You are so quick today. So hypothesis testing is one-tailed and two-tailed. If it's one-tailed, what are the two types of one-tailed tests? Right or left? Right. Yes, one-tailed on the right side or the left side. What's two-tailed? Both sides. Thank you. And now for the people who are a little bit later than everyone else, go. No? Okay, done. So in every case, your null hypothesis, your underlying hypothesis, your status quo hypothesis, H naught, H0 is always what? Yes, I know, but mathematically, it's always what?
0.5.
No, 0.5 is just all the examples we did. But there's something about every one of them, every null hypothesis. It always gets the equal sign. If I come along and I say, you know, up until now, my winning percentage has been 60%, but I think it went up, then my null hypothesis will be P is equal to 0.6. because up until now it's been 0.6, and I'm testing to see whether or not that changed, right? Usually it's 0.5 when things are fair, but does not have to be. So it's important to read the question to understand what the null hypothesis is.
So every null hypothesis always starts off with equal, it's always gonna be equal.
And the alternative hypothesis always gets the what? What are the three possibilities for the alternative? Greater than, less than, or not equal to. Excelente. Greater than, less than, or not equal to. Greater than and less than corresponds to what type of test?
Right tailed or left tailed.
Okay, and not equal to corresponds to what type of test? Two-tailed. That number that we're claiming, according to the null hypothesis, to be the true value, p equals 0.5, p equals 0.6, whatever the case may be, how do we denote that number symbolically? What symbol do we use for that number that we're claiming the null hypothesis says that p is equal to? It's not p, it's not p hat, it's not p twiddle, it's not p star. Which one? No, p value is something else. No. No. When I have a null hypothesis, yes, if I have a null hypothesis, I'm claiming p is equal to some value. That value that I'm claiming that p is equal to versus p, let's say, not being equal to that value is a two-sided hypothesis. That value is p0, p naught, p null, something like that. So we have p hat, we have p twiddle, we have p star, and now we have p sub 0. 5 different things that p twiddle, x plus 2 over n plus 4. Number of successes plus 2 over number of trials plus 4.
Is there a formula for every different variation of p?
No.
How many
Or
variations?
just the one that we're?
Oh, just 4, but I just had a lot of fun doing this. P star has 1, p twiddle has 1, and p hat has 1. P naught does not, and p does not.
And those three p variations are the kind of formulas that we'll be using.
That you'll be using, yes. How do we go about and actually perform a statistical test? How do we do it?
One prop sequence.
One prop z test if it's a proportion test. We might not have done any other ones yet, but we will. But in general, the answer is don't do it by hand. Use your calculator. So you're looking for the one proportion z test if that's the situation that we're dealing with. Yes.
Are we gonna use two prop sequence?
Yes, we will.
But not now.
Not now.
We haven't done it yet.
That's it. So all we have so far is the one proportion z test, the one proportion z interval. When you perform a statistical test, there is one number that comes out at the end that you're going to base all of your conclusions upon. What do we call that one number? The p-value. So again, we have p, p hat, p star, p twiddle, p naught. And now the p-value. What do I do with the p-value to make my conclusion? Of course, where do I get the p-value from, by the way? The calculator will give it to me, right? So what do I do with that value? What do I do with my p-value? Yes?
So if it's smaller than your level of significance, you reject the null hypothesis.
What if it's not smaller?
It's not rejected.
Wow. Usually 0.5, 0.05. So if the p-value is low, what's it? If the p-value is low,
You let that hypothesis go.
the null must go. Come on, it rhymes. If the p-value is low, the null must go. If the p-value is high, let it fly. Go eat some pie. Hi. What's up? You him. But you too, hi. What do you want?
So this is after you do the one problem test.
Yes, of course. How do you get your, huh?
If it's lower, it's garbage, if it's higher, it's good.
If it's lower, it's garbage. If it's higher, what's garbage? What does that mean? See, in a real situation, maybe you want the null hypothesis to be true. And in which case you want to reject the alternative. Maybe you don't like the null hypothesis. Every problem is different. There's no emotion in this. The math speaks for itself. You can't come in saying, I'm hoping for this outcome. Because if you want a certain outcome, you can possibly skew the data in the direction that you're hoping for. Right? Let the data speak. If the p-value is less than alpha, the level of significance, the squiggle, the fish, then we reject the null hypothesis in favor of the alternative. If the p-value is not less than alpha, not less than the level of significance, then we do not reject the null hypothesis. We stick with it. Whether it's right or wrong, we stick with it. Any other questions? There were a couple other formulas that we did, but I'm not gonna, if you have your calculator, you don't have to worry about them. But on your cheat sheet, if you want to write them down in case your calculator magically breaks at the last second, or you run out of batteries or something, then there is a formula on page 383, which allows us to calculate Z. Z is nothing more. When you have the null hypothesis, and you believe the null hypothesis is correct, you take your p hat, which is your actual value that you got from your data. You subtract the mean, which according to the null hypothesis is p naught, p0. You divide by the standard deviation, which according to the null hypothesis is p0, 1 minus p0 over n. Essentially what you're doing is you are calculating your z-score of the data. This formula is nothing more than data point minus mean divided by standard deviation. It gives you your z-score. From the z-score, you can either go to the table or your calculator and calculate the likelihood of being past that. That is your p-value. Your p-value essentially is the likelihood of being more extreme than the value that you actually got. This is the formula that your calculator uses to compute your p-value. Yes?
So it's minus p0, not p hat, right?
No, because for hypothesis testing, we have a hypothetical assumed value of the mean. Because we have it, and we work under the assumption that this is a true value, we use it everywhere. See, for confidence intervals, what do we add and subtract for confidence intervals? It looked like this, but there was one major difference.
C star.
No, for this part.
P hat.
We use p hats for confidence intervals. Huh?
That's for which one?
For confidence, because we don't have p0 for confidence intervals. We don't know what p is. We don't have a belief. We can't use it. But here we do have a belief, so we use it. For hypothesis testing, we use p0 here. For confidence, yeah, we're almost done, okay? For confidence intervals, we don't. Yes?
The confidence level, like by default, is it 0.95%?
If they don't tell you, what to use, the confidence level is 95% and your level of significance is 5%. If they don't tell you. Otherwise, use whatever they tell you. So that's it. That's what the test, it's all easy, right? We covered the entire thing in one period. Right? You gonna get 100%?
No.
How about you? How about you, Andrea? What?
What?
Amaya? Come on. Calvin, 100%, right? Yeah. Okay. Peter, I know you will. You have the stuff down cold. Yes. Who's gonna get 100? Come on, confidence. That's right. Hey, it's easy, guys. If you want 100, you know how to do it. That was off camera, so don't worry about it.